Section A7, working with units. So now we're going to work with units, and we're going to start with a principle I learned from a chemistry professor, Dr. William Kreiner, when I was a freshman many years ago at St. Joseph's College in Philadelphia, USA, in the fall of 1968. Last I checked, he's in his 90s. And here, the first part is the trick. So let me show you the trick. We're going to divide this into like 4 sections. Section 0 is the trick. And the trick involves clever use of the concept of unity. Unity is 1. When you multiply by unity by 1, you multiply anything by 1, you get the same thing back. You're not going to change the intrinsic value of that, because 1 times 5 is 5. So 1 times 6 is 6. But what you do here with this trick, you can change the units. For example, 1 hour equals 60 minutes. Now, if you divide both sides of this equation by 1 hour, you get 1 is 60 minutes divided by 1 hour. If you divide both sides of that equation by 60 minutes, then you would get 1 hour over 60 minutes equals 1. So here, since 60 minutes per hour, when you divide that, it's basically 1. You don't change the intrinsic value by multiplying by 1. So if I have, for example, 2 hours, I can multiply that by unity. I won't change the intrinsic value. But if I multiply by this form of unity, 60 minutes over 1 hour, then the hours cancel, and I get 2 times 60, 120 minutes. So I find that 2 hours is equivalent to 120 minutes. So I change the units by this trick of multiplying by unity in the appropriate fashion. And now we're going to do 3 examples of this. Okay, question 1 is going to be an analysis with text. So say we're given that 1 byte exists per character. There's 1 byte per character, and a character would be like a letter. Estimate in megabytes the storage for 400-page book. No photos, just characters. Okay, so what we do here is we may not understand the details about megabytes and storage, and it doesn't matter. It's just the power of the dimensions and the units. We want to know how many characters, say, are in the book. I may just write down something like characters in the book. And now I start thinking, well, wait a minute, how many characters are there in a line? So I can figure that out first, characters in a line. This is the logic. Then how many lines are there on a page? And then how many pages are there in the book? So that's my logic. That's how I'm thinking this out. So here I would have, if you just count or just count how many characters there are, and spaces would count to from left to right, just count how many in a line, you'll find there's about 90. There's about 90 characters in a line. Then if you were to count, now there's no pictures, so we're basically looking at text. So you're looking at something like this. So if you count the number of lines per page, you're going to get about 40 lines per page. And the problem stated you're going to have 400 pages per book. All right, so with the numbers in there like that, you're going to work this out, multiply this out with calculator, and you're going to get 1,440,000 characters per book, and each character is a byte. So really, you have it. This is basically 1.4 megabytes. Right. Now, when I do estimates, I'm not going to worry about 1,000 versus 1,024. Sometimes I'll put it in if I want to be a little more precise. But if I'm doing an estimate like this, I'm not going to worry about it. In fact, if you were to like convert this, go ahead and do this. This is 1440000 bytes per book. The way you would convert, you want megabytes, then you put down here bytes, and you would need here for the megabytes, you would need, well, you could do it in two steps. You could say, well, suppose I did kilobytes first, all right? Then 1 kilobyte would be 1024 bytes. And then if I want to get rid of the kilobytes, see how I put the kilobytes down there so you cancel, and then I have megabytes, and then I have 1 over 1024. So if you want it, you could do that, but you'll still get to like two significant figures. You pretty much get like the same thing, so not going to worry about it. So it'd be 1.4 megabytes. That's it. So if we have the books, number of books, one book would be 1.4 megabyte. That's the storage. And then 1,000 books, you can just make this gigabytes. And then 1,000,000 books, 1.4 terabytes. And then 10 million books, 14 terabytes. And I want to go for 40 million because that's what the Library of Congress has, about 40 million books. So if you multiply by 4, you get 56 terabytes. Man, look at that. 40 million books. Okay, we want to do next images. And if we do images, we're going to have the problem say, what's the storage? What's the storage in kilobytes for 800 by 640 pixels with 24 color depth, 24-bit color depth, and a 1 to 10 JPEG compression. So the nice thing about these is that you don't really have to know the details of the computer science, and you just take the given and we work it out by common sense. We have 800 by 640 pixels. And we know that there's 24 bits per pixel. And the problem is going to give us also that a byte is 8 bits. All right. So therefore here I would have 1 byte per 8 bits. Note how I arrange the bits to cancel. The pixels are going to cancel. And then if I want to get rid of the bytes here, this byte, to get kilobytes, then the 1 kilobyte is going to be 1024 or 1,000. And then I need to have a compression ratio of 1/10 for JPEG. So if you multiply all this out, you get 150 kilobytes. Isn't that nice? So now if we have a book, let's just look at a book with 40 photos. Then if you have 40 times 150 kilobytes, 4 times 1560, and you have the 2 zeros there. So you have 6,000 kilobytes. It's about 6 megabytes. That takes up a lot of space, see, because the book that we just did, we found that the book would have 1.4 megabytes. So if we add this, you get like 7, and let's just round it off to 10. So 10 megabytes would be the book that has 40 pictures. So then just for fun, what I did here is made a little table. Then if one book has 10 megabytes, 1,000 books would be 10 gigabytes. And then 1,000,000 would be 10 terabytes. 10 million would be 100 terabytes, and 40 million would be 400 terabytes. The next hard drive level would be petabyte, peta, and this would be about half a petabyte. So if you had a petabyte hard drive, you could have like Library of Congress in your pocket. Isn't that nice? Okay, let's do another example. Let's do audio. For CD sound, it's given that you need 16 bits per channel, and in stereo, you're going to have 2 channels. So per channel, and stereo is going to have 2 channels. And the sampling rate is 40,000 per second. Estimate the storage. What is the storage for 70 minutes of music? Now, I intentionally picked things that we're not familiar with, sampling rate, storage, because the power of the units and dimensions, we can solve any problem, like in any field, by being guided by the dimensions. So for example, you have 16 bits per channel. I need to cancel the channels here. I got here channels. I got 2 channels that I have to deal with, and I could have here 2 channels, per sampling. And I have 40,000 samples per second. And you can see now things are canceling. The channels are going to go away. The samples are going to go away. And then to get bytes, I want to get rid of the bits. So I put the bits down here. And I want to get bytes. 1 byte is 8 bits. And then here, if I want to go to kilobytes, I divide by 1024 bytes would be 1 kilobyte. So the bytes cancel. And if I want to go to megabytes, so I want to cancel the kilobytes, it'd be another 1024, like that. And then if I look at this, everything canceled. The seconds didn't cancel, but then I didn't use my 70 minutes. So if I have here 60 seconds per minute, that will transform this into minutes, and then I multiply by 70 minutes, then I'm all set. I'm all set. And see, it's the cancellation of the units at each stage that is my guide. And you get 640 megabytes, and that's what a CD holds. Like, we got the result. A CD is about 640 megabytes. That's amazing. And then if you have here, let's say, if you look up, you find 650 megabytes for 74 minutes of music, which gives you 8.8 megabytes per minute. And if you do the compression, you can get this down to about, with MP3 compression, you get this down to about 1 megabyte per minute, so that a 3-minute song is going to be 3 megabytes. Now, back in the early 2000s, Apple came out with the iPod, and if you take the iPod here, and you have a hard drive, there's 120 gigs, so you have 120 gigs on the iPod, 120 gigabytes, like this, and one song is going to be 3 megabytes. Then I want to get rid of the gigabytes and the megabytes. So my guide is, I want this to cancel, I want this to cancel, so then I have to put in 1024 like this. And that's about 1,000, and this is 3 into 120 is 40, so you got 40,000. You got 40,000 songs. And that's pretty impressive. You're jogging, with this thing, and you got 40,000 songs. Each one's 3 minutes. You're going to do a lot of jogging before you're going to hear that song over again, repeat. All right, 40,000 songs. Wow. One more video. And here, for a DVD, we're going to be using, this is given, 720 by 480 pixels per frame. And it's given where you have 24-bit color. And we have 30 frames per second. And we have compression given as 1 to 40. So it's going to be, in other words, 1 over 40 for the compression. Find the gigabytes we need for a 2-hour movie. I start with 2 hours. You can start anything you want. You can start with pixels if you want. I'm going to start with 2 hours, and then I'm going to multiply by the 720 by 480 pixels per frame, and that's going to clue me to get rid of the frames. So I need 30 frames per second. And now the second and the hours, I want to get rid of that. So put the seconds up here to kill the seconds and the hours down there. And I need 3,600 seconds for 1 hour. All right. You could break that up into 2 parts and have here, if you want, 60 seconds per minute. And then here, 60 minutes, per hour. The minutes cancel, it's the same thing. And then here, what do I have? I got the frames canceling, and I need to get pixels. I need to get rid of the pixels. So I put the pixels down in the denominator so that they're going to cancel. And I see that there's 24 bits per pixel. All right, per 1 pixel. And then I want to get rid of bits. So I want gigabytes. So I have gigabytes and I have bits, and that would be 1024 cubed for the bits. You can do it in steps. If I want to go to kilo, I divide by 1024. I want to go to mega, divide by 1024 again. I want to go to kilo, I divide by 1024 again. So that's cubed. And this is not bits, by the way. This would be bytes. So this is bytes. So now I got to get rid of the bits and the bytes. So here's how I do that. I want the bits down here to kill that bits. I want the bytes up there to kill that bytes. And I have 1 byte is 8 bits. All right. So that should do it. I need compression 1 over 40. Multiply it all out. You get 5 gigabytes, which is about what a DVD can hold, like 4.7. And if you were to put the audio in, you would find the audio doesn't contribute much at all, because remember, for the audio, we had 640 megabytes per 70 minutes. And if you want to go with 2 hours on that, that's 120 minutes. And if you do 120 minutes on that, you're going to get here something like, so if we have 1 terabyte and we have 1 movie is 5 gigabytes. The book shows you how to handle the audio with some compression, and it doesn't really add much. It's going to be 5 gigabytes basically. So then here I want to get rid of terabytes and gigabytes like this. So I need 10, 24, 1. And here you can see that's 5 into 1,000. It's going to be 200 movies. So 1 terabyte gets me 200 movies. And Amazon Assistant says there's about 500,000 movies in existence. So let's see, if you multiply by 1,000 to get 200,000 movies, that would mean I need to have a petabyte. Now, not all the movies are 2 hours, so that's actually coming close to taking care of everything. 1 petabyte. Now, can we get a petabyte? Can we keep going? Well, our guide is to look at DNA. And if you look at DNA can store 100 petabytes. So if we can figure out, like what nature's doing, because DNA is very small, like in the cell, if we could figure out how to do stuff like that, then we're in reach. You could have something in your pocket that would have all the movies, like 500,000 movies or so. That's wild. So it's a kind of cool little sense of scale here, showing the DNA, and here an insect and like a football field or Indianapolis Motor Speedway, for example. And this is sometimes referred to as nanotechnology. Nano, by the way, is the metric prefix for a billionth. A billionth with a TH. So in other words, it's 1 over a billion. And since a billion is 10 to the 9th, this would be 10 to the minus 9th. So a nano is 10 to the minus 9th. So, but probably in the future, as today we're moving in this direction, is that we will just pull things down from the cloud. So we won't really need to worry about having things in your pocket, since the cloud will have all the movies and just pull down as you need them and to view them. All right. Last thing we'll do in this chapter is talk about calculators and types of calculators.